All right, so before recording, we discussed about the midterms, and I created a poll saying how many students, if the you have enough time to appear or the finish all the questions. I think majority of you have enough time. One student could not finish. No, I hope that in future, whenever you need more times, always send email. Okay, send emails or beforehand if you feel like you need more time. Always, for this case, I'll never say no. But obviously, you have to be reasonable in terms of you will not ask for 2 more extra hours. Um, but I think most of you probably sufficient time. And again, for quiz or anything, if you could not appear quiz or something, always send emails and ask. If you don't ask, I'll never know that you have difficulties. I noticed that some student didn't take exams. I have no way to know why you didn't appear the exams or meet quiz. So don't give up anytime. Anytime you need something, always ask. Um, all right. So, and second thing is, I noticed that this class has nearly 60 students or 50 students, and 16 or 17 of you are attending every day in the class. So appreciate that you're coming so that I don't have to speak to the computer all the time. Um, but I think it's helpful. It's very helpful. But I know that you don't have to. No? You don't have to come here. Now, if you don't come, I will not complain because I know that there are a lot of other things you have to do, and it's being recorded, so you can always watch before later. But I do appreciate that I see your face here, so it's helpful. And second thing is, I know that many of you register for CEE150 159. That's a green infrastructure class. Green infrastructures. That's the one I teach next quarter. Um, one of the things I want to say that there is a requirement CEE 150, but that's not a requirement now. Okay, and the reason is before C153, it was not covering some topics that needed for this class. Now that is, if you took C153, you don't have to worry about C150 as a requirement. Okay, so if you are waiting for C150, don't worry, that's not needed at all. All right, so these are the assignments due or in futures. Those are the things. As you see, there is no homework due. So that means that's by design. You are not supposed to do any homework after week 5 because you are expected to focus on the project writing. So there will be one quiz which is needed. The reason it's needed is so that you at least pay attention to the materials we cover after the midterms. So that's the reason we have that quiz. And again, you will notice that you have best 3 of 4 quiz. So if you already did well in the last 3 quiz, even if you don't take this quiz, nothing will happen. I'll take the best 3 of you of 3 the quiz. So this is a low key in that way. But if you have not taken other quiz, or if you need one better quiz than the one of those, then you should take this week quiz 4, which is on week 9. I set the time, Thursday next week, and everything covered after the last quiz, material that's not covered in the last quiz will be part of this quiz. And project draft is due on the Monday or Tuesday of the last final week. So yeah, basically I want you to have it by that day so that I should be able to give you some feedback by Thursday or Friday. And that way you spend one day, finish, just address the comment and submit. So the closer, the better the draft you have, the faster you can get the final draft, because ultimately you just have to change a little bit and then submit. So you can submit the final draft as final papers anytime before the Friday of the final week. So you don't have to wait until Friday, and your goal would be just addressing my comments. Your goal is not to do a lot. My most of the cases you already written the draft as a final, almost like a final, like any other class. So you should just address my comment and submit. Don't spend too long if the comments are not there, a lot comment. Okay, so projects meet me if needed to get quick feedbacks. All members do not have to meet same time. As a team, you can meet whoever wanted to meet, and you can communicate with your team members, and you can record that meeting so that you can share with your team members. So that way you don't have to, everybody doesn't have to have a specific time commitment. And now it's time about write. The more you write, the faster you get to your draft, and you can send a rough draft. So one of the question was syllabus. It was February 25th. I realized many projects, they are delayed by their outline. They are still revising their outline. So I wanted to be sure that you have enough time to write the draft. That's the reason I extended it. Otherwise, it's supposed to be 25th this Thursday. So I extended this one for 1 week because of that reason. Or 1 week or before. Again, your goal is not to wait till the end. Submit before that. The reason, as soon as you submit, I give you feedback, you are done with it. You finish your final draft, you submit before even the last class. Then you don't have to worry about this class again. So I think I encourage you to do that. That the extended time is already given, just so that you don't have to think of all that issues. Right. So again, you should share with your friends or colleagues so that you have feedbacks from them before you share with me. All right. So this is the quick quiz 3 results. As you see over here, the most of you got. I think this is 9 questions out of not 10 questions. So the numbers are a little bit skewed. So that means each questions carry more weightage than the normal quiz. So if 1.1 or something. So in that context, you can see the grade. But average is 90%. Okay, 89%. That's the average. And you can see the distributions. So any questions so far on quiz or anything else?
I have a question regarding the video. Does every member need to make an appearance in the video?
No.
Okay, thank you.
So again, you all should contribute in the sense that you should create a slide, create 1 or 2 slides based on what you wrote, and then all members should decide what slide to go to the final, because it doesn't mean that you have to present 20 slides. You can decide that. But one is fair if one person present is fine. But I think it's better when more student presented because that just shows it's not like it's a requirement. But as a team, you should tell that everybody has participated. Okay, everybody should have contributions in some way or other. And I have also presentation from last year where they all presented in the sense that they have their slides. They practice for that 1 slide or 1 or 2 slides because of Zoom automatically will record you just everybody is non-muted, and the next person starts speaking, it will show the person face, and or you don't have to show the face. You can always hide it. It's up to you. But it's going to be on the public in the sense it's going to be uploaded in the class website. So just be aware of that. Okay. And I'll also share the last year presentations. So what you can do is you can always record it and send me share the file so that I can upload it. If not, you can share on your own YouTube. I'll just provide a link to the rest of the students when I send the finals. Usually I share with all the entire class. as an email. So it's fine if you just share the video so that I upload, or you upload by yourself and share with me the link. Right. So now, as you see, last class we learned about landfill and all that. But when you come to calculation, how much energy you'll receive, you'll get, all that's needed some kind of calculations. And most of the time, you can calculate thermodynamically and by using the redox equations. Okay, so those energy is there, but energy has its own unit. How do you know how to compare? All that you have to have some background. So what we're going to learn today is mostly energy fundamentals and a little bit of applications of how you can get energy from algae, but more of a broad concept. For many of you who have attended, at least the grad students attended a seminar today, um, which is on using algae to remove nutrients from wastewater. So I shared that video already on the class website or the YouTube channel. You should watch that. So this is the first half. So that's part second half of the class. So I'm going to finish the first half in next 30 or 40 minutes. Then we can end the class. You can watch that video. It's already uploaded on the class website. All right. So waste to energy. As you see, this is the signature of the waste, the energy that we need in US. As you see, most of the energy comes from petroleums, and coal is diminishing with time. If you see that pie chart, and uh, and mostly the natural gas is increasing because of fracking and all that aspect. And renewable is very small portion of it. And so that renewable energy can effectively grow with time. And so that's the whole idea. When you think of waste, you can start thinking of how you can get energy out of those waste, mostly the bio waste. So if you think of biomass, when you see biomass, that's a source of energy, because think of what that biomass is. The energy, every energy that you see over here, that all start from, if you think of, let's think of if you track, go backward and backward, where the energy, the source of energy of everything that we are getting. Let's start with that concept. Let's start with something what we get now. Let's say petroleum. Where the petroleum got this energy? Anybody who can? There is a question. Why does nuclear power make up such a small percent of total energy? If because of the perception, I think nuclear is the one of the most cleanest energy in terms of water as well as the waste, and in terms of volume. It's one of the safest because it's because of nuclear there are so much other um, precaution people take. So usually they are more regulated, so that's why it's the chance of accident is low, but it's not zero. But when there is a accident, the the effect is devastating. And as you can see that in Japan, because of the earthquake, and earthquake happened. After that, there is a tsunami. So if you see that didn't the nuclear power plant didn't fail because of earthquake. It fell not because of even it fell because of tsunami. And even tsunami could not have failed that power plant unless they put the entire the pump the any power plants, you have a coolant. You supply water, cold water, so that you cool down the energy. And so that coolant was driven by a power pump, a pump that drive that water. And so that pump was all on the downside below the sea level. So anytime the tsunami comes, they break that barrier, and then the entire area is flooded. So if they would have put the pump a little bit higher, this thing was not have been failed. So as you can see, they learn a lesson there. And the reason they put the pump downward is because when you drive the energy, the pump water from ocean, if you put very high, then you are going against the gravity. So you are spending a lot of energy. So they just want to save money. They just think that this will never fail. So that's the reason they did it. So as you see, Very rarely nuclear power plant fail, very rarely nowadays. So I think, this is my obviously opinion. I am not expert in that area, but renewable is the one of the safest, or the nuclear is one of the safest form of energy. And instead of having us this, the nuclear bomb, all these things people have, all the country has, they can power the entire, energy sector for many years to form. So you don't need even any energy if you just use the nuclear power plant. What's the point of having all these nuclear weapons and all that stuff? Nuclear power plant doesn't even require that much purified version of nuclear energy compared to those bombs. So again, this is just another thought. We are talking about energy harvest. Why not use all the turn all the nuclear weapon into energy and actually use for things that is matters. So yes, it's a I don't know why it is such a small, just the perception, public perception, regulations. Maybe that's one of the reasons. Okay, so the point is, let's start with here now. Let's start with the petroleum. Can we trace back which form of energy that it come from? Because energy transfer from one to another, you learn that. Let's start with petroleum. So what is the energy in the petroleum? Can anybody says what form of energy inside petroleum? Like let's say, when you burn the petroleum, you get thermal energy. Okay, so that's the thermal energy when you burn it. And thermal energy, so if when you heat it up, um, oxygen, it become fire, right? So that's CO2. So you convert to thermal energy. And thermal goes to, um, it moves something, to move the turbine or anything that gets you electrical energy. So this thermal translate to mechanical, and then mechanical turns to electrical, and then electrical goes to um, other form of usable energy for us. So what is in the petroleum? What form of energy it is? It's the chemical bond, that bond breaks, right? So petroleum, when you burn it, it becomes CO2. So carbon becomes, so that bond has the energy. So that's the chemical energy. So where do petroleum get that energy from? Where it get from? So think of where we produce petroleum to begin with, how it is being formed in the millions of years ago.
Isn't it from like a lot of compression over time, and it's
So the
kind of like made
biomass,
out
right?
of
So
yeah,
the,
yeah.
the dead biomass, it's been compressed over years, millions of years. That's how it decompose or become petroleum. Okay, so that's basically the energy is in the biomass, right? So that's also a chemical energy. If you think of our body or trees, those are chemical energy. But where they get it from? Where we get the energy?
Sun.
Exactly. So we get energy from sun, photosynthesis. So that's biomass, get it from sun. But how sun energy transfer from there to here? They don't have a conductor, right? So we don't really have a conductors to send the energy. So how sun send that energy to us? What form of
Radiation.
energy it is? Yeah,
Oh,
one more.
radiation.
Radiation. So that's the electromagnetic energy, right? Okay, so electromagnetic. So light is electromagnetic energy. So that's the electromagnetics or photons. Okay, um, or photons. Because electromagnetic itself is not a electromagnetic wave. It's not an energy form. It's a wave form. But if you light can be a wave or it can be particles, right? So that particle is photons. So that's why the energy is um, H nu. Okay, nu is the frequency, H is the Planck's constant. So that's the energy of a photons. Okay. All right. So where the sun get its energy from? One guess. Whoever get that guess, they'll get a without anything else anymore.
Isn't it like hydrogen in the sun? Something like that.
Yeah, but what's that energy? What's that? There is some chat window, so let me check. What happened in the? Yes, exactly. You right way. So what is that energy called? Yes, it's a nuclear energy. Okay. So that inside we have nuclear, because every atom has energy because the protons are positively charged. So when you imagine this positive charge, they should not be close to each other. But in nucleus, extremely compact place, protons are close to each other. The reason they are close to each other is something is binding them. That's the nuclear energy. Okay. So the moment you break them, or fusion, either of them, you release that high amount of energy, and so that's nuclear energy. Okay. So now that you know, this is actually a quiz question. So the reason I'm putting this exercise is you have to. I'll share you. I will share um, one pictures then in the quiz where you'll show what energy is being transferred to what energy. Okay, so that's the quiz in the quiz 4. So this is just example that as you see, every time you transfer energy, it comes from another. So we can thank everything to nuclear energy. So that's the reason if you see our body, no life would have existed without that nuclear energy. Carbon would never form unless that nuclear bomb going off in on sun. So those hydrogen combine to helium, helium combine to next one, that's combined to carbons, and it goes on, and then it form after like certain mass, you will not form anything uh, beyond iron. You will not form in the sun. So the sun is cooking all these bigger atoms. So that's why, if you think of why the core of Earth is iron, is because of it can combine and become iron at the end. But beyond iron, you cannot form inside the star. In fact, it's extremely hard also to form iron. So beyond that one, to form things, the Earth has to die. Not Earth, the sun has to die. Because with time, it become heavier and heavier, and then all those bigger and bigger mass becoming at the center of the sun. The reason sun exists is because of nuclear energy. They brush together, and then fission things happen, fusion happens, and so it form bigger and bigger. And with time, the sun's center become heavier because all this iron and all that. So that's why, after a point, the nuclear energy hold the sun together, and the thermal energy because of nuclear, they push them apart. So that's how things steady place. Otherwise gravity is going to become super and super compact. After a point, it becomes so heavy, the gravitational pull is extremely high because it's very small amount, lot of things, and then it will collapse. Okay, and that's how the whole starburst happens, supernova explosion. And that's the reason, that's how the sun dies. And then during that explosion, so much energy is there though, so that all these ions will start binding with each other to form the larger atoms. So without this earth being the sun die, none of these things that you see ever existed. We will not have a life without death of a star. So if you think of where we come from a dead star. Okay, all the elements that we use, everything, that's because there are many stars died over billions of years or longer to form what we have right now, all the elements that we use. So again, if you think of philosophically, all this energy coming from nuclear energy. So it makes sense. The question is very timely. Like the person, William, you asked this question: why does nuclear power doesn't make up such a large portion, and that's the question to ask too. That's we get all our energy from nuclear. We have everything we need. All the if nobody produce atomic weapon or nuclear weapon, we should have all the energy without clean energy, without anything to do worry about. But we are human. We are doing a lot of stupid things. This is one of those. Okay, so apart from that, as you see, the biomass contain a lot of energy, and we can transform that energy a lot. Okay, um, so now question is, we already covered that one, how the energy transform. As you see, sunlight, the nuclear energy transform as a electromagnetic or photon energy, and then plants photosynthesize, where they combine carbon dioxide with water and sunlight to produce glucose. And as you see, this sunlight is transformed to this chemical bond in the glucose, the biomass. Then all the bigger things form. When we take that one, we also decompose that, we get energy. That's why we eat. And then some animal eat those plants, and they also get energy. And also we eat meat, and it has more energy, So that's how things energy is being transferred from the food. So now for us is to bring it back, how we can take back this energy without going through all this process. So one such example is algae. As you know, algae is a bigger concern in many areas because of excess nutrients. And when the algae grow, like you see in this picture, it's so dense. It's a plant, or it forms they can photosynthesize. So it's not a plant, but they can photosynthesize. So that means they can capture that solar energy. But then in returns, these algae also die with time. And when they die, they create this biomass, excess carbon, which create anoxic zone. So one of the things like people initially thought, or the perception was, algae is a synthesis organism. So that means it creates oxygen. So if you have algae, you have more oxygen because they are creating oxygen, taking carbon dioxide out of the water. So you should have more oxygen in your system because you are producing oxygen by algae, which is true. But until the algae start dying, once the algae sufficient biomass is there, they die. All the other bacteria will start growing there, and then those dead biomass, because of their growth, bacteria growth, they consume all the oxygen produced by algae. Not only that, they will consume everything else too. So they produce a lot more very low anoxic zone. Because of that, it kills fish and all that stuff. Algae also produce neurotoxin. That's why any water system which has, let's say, lake, that lake is used for drinking water treatments, drinking water. If there is algae grown there, you'll produce this neurotoxin. It's very difficult to remove by wastewater treatment plants. So that means if we are consuming those water, we are taking those neurotoxins. So that's why it's a big deal. And there is a reason why we want to remove nutrients from these lakes. And so now if you see, algae can be used as a solution as opposed to a problem. And the difference is, instead of growing algae uh, in nature, we should grow algae in-house with the waste that is produced at the locations. So the example here, algae can capture the solar energy, they grow, and you can take those algae and produce ethanol or methanol, and then also you can extract oil from it and produce biodiesel and all that other stuffs here. So again, this is a renewable source because it captures the solar energy. You can clean water, so that's a renewable source. You capture energy from solar, that's also renewable, and you produce biofuel. Even that ultimately it becomes carbon dioxide. It is coming from a renewable source. So this is a very attractive method. And I know that two different projects in this group, in this quarter, you're working on, either you are directly using algae or you are indirectly thinking of algae as a comparison. So this is how the algae to grow. It's all it need is a nutrient-rich wastewater. You cannot grow algae in a very low nutrient conditions. The reason is other bacteria will outcompete algae. So you need very concentrated nutrient-rich solutions. And you get that either in wastewater or in agriculture waste, where you have lots of these fertilizers and all this waste. So you got those two. And then you have to get algae. Those algae is important to get from the location where you are getting wastewater from, because naturally algae grow in that system. So you have to harvest those algae from those systems and reuse them, as opposed to use synthetically growth algae. So I know that one of you guys asked this question, micro versus macroalgae. I didn't know that difference. So I used that your question to ask the seminar speaker today, and I say what to use. And the seminar speaker says, it doesn't matter what's micro or macro. What they need is the algae that grown in that wastewater originally, because they have evolved with time. They are more acclimatized with the conditions. They will survive. Then next thing is you need sunlight, but you know that 24/7. Unlike a wastewater treatment plant, which can operate 24/7, sun only lasts for 12 hours or so. And many locations you may not get sunlight, so that means you got to have extra energy from you can use energy from the on the LED lights. Okay, so that's why you see in these pictures, they have lots of light inside the system. Also, watch the seminar. I uploaded. You'll see all these discussion there, as well as the how it is done in the large scale. Last thing is infrastructure. Infrastructure, what you can control. You can control the flow rate, because that flow rate determines how much exposure of lights that algae get and how long the kinetics of it. And you have to have a system to filter algae from water, so that you can reuse them, or you can filter them for biodiesel or other applications. So all that in the seminar. Again, the link is given here at the bottom, but if you already have the class website, you can see those there. Again, the same idea. You use algae to produce clean water and oxygen, and the algae can be used to as a source of energy too. Source of energy, biodiesel, and all that. Methanol, you can also produce methanol. And this is just to show the pictures how it works. As you see over here, they are basically a linear system. All it does, it moves around, because you need many takes long time. Let's put it this way. This is not so your retention time is the key, and the only way you can achieve retention time is basically having this pipe that goes so long, like miles and miles long pipe, so that by the time it get to the last stage, it has all the algae formed. So that's the way they create the circular systems over here. So it has very high footprint. So that's another concern to think about, is because that light exposure is needed, you cannot have a deep water. So you have to have a sufficiently thin enough light so that light can pass through it completely. And so this is the system. They have tube light is over here. This connection has tube lights or the LED light, so that expose that sunlight to them. So this is indoor, so that you can control the temperatures, because if you are doing it in the cold climate, the efficiency will be low. So all that extra energy is needed for that. So ultimately, it can be energy positive if it is in a climate like California. But also, another thing to consider is how we can combine both sunlight as well as indoor environment. And this particular picture is in a cold climate, so that's why they put it inside. Again, just watch those talk. Any question? All right, so let's do one thing. Let's take a 5-minute break. When I come back, we just go through energy fundamentals, just a simple calculation you already know. We'll go through that quickly. We'll meet. This is now 4:43. Let's meet at 4:50. So I'm going to pause it. All right, so I forgot to record the things that we cover. I just want to read this one. This is basically covering what's the force, what is work, what is energy, what is power. Power is energy over energy over time, and energy. You know that this is joules. Joules is the energy unit of energy. Work is force time displacement, and force is mass time acceleration. That you learn on in physics class. So just connect those together as a refresher. This is just I explained that 1 watt equal to joule per second. And here is a question. Here we gave you energy. This is energy here, and I also give you the time. How much energy is produced per time? And I ask you what is the power. And power is energy over time. So you just put the number and you convert to watt by unit conversions. These are again a different form of energy, gravitational potential energy. That's because how high the water is stored. Thermal energy, how that's basically example is boiling water. Chemical energy, think of every biomass has chemical bonds. Cells are basically bond energy. Nuclear energy stored in every atoms. When you break the atoms or fuse together two atoms, that's the energy is released. Electrical energy is very common. That's what we learn every times. We use every form of electrical energy. Electromagnetic or photon energy, or photons that translate in sunlight. So if you think of different form of energy, the reason nuclear energy, electric energy is used because that's very easy to distribute, and so that's why you see this electric wire and all that. And then you have to think of why it is distributed certain way. There is always a loss of power or energy when you move. But then you have to think of delivery, how quickly you can deliver. Think of gasoline. If you're think of you're driving a regular car versus electric car, how long it takes for you to recharge your entire energy. Gasoline, it takes only whatever, so 10 minutes or 10 minutes too much. Maybe 2 minutes we can fill the entire 5 minutes maximum in a gasoline stop. So let's say 5 to 10 minutes you have to stop at a pump stations. Electric energy, if you think of a battery, to recharge, currently if you have really, the excellent Tesla and the power mode, it takes 30 plus minute to fully charge a electric car. I'm pretty sure with time this will change, but there is a limit to it now, the delivery of energy. So that's the big constraint between here. I would say 10 minutes is too much, 5 minute maximum, including sitting or standing there. So think of this as a constraint. Every time you have to design the systems, you got to deliver the energy very quickly in terms of delivery. Again, as I said, discuss different form of energy. Kinetic energy, how the formula is mass time velocity square, so half mv square. If it's rotational energy in the turbine, that's I times rotational velocity, omega. That's what we write, W. And this is inertia, mass of the inertial mass. That's again, we don't need to go through this. This is all physics. So I'm just going to put the equation here so that you can understand. So that's equal to, it's like a center of mass, how you use that mass energy. So mass times r squared divided by 2. So all these things are given. So I don't expect to remember any of these. Just know those, how do you connect them back if you need it at any point. So let's have examples so that you can see how to use those equations. What is the kinetic energy associated with 15 kilograms of automobile traveling at 100 kilometers per hour? So basically, this is the mass of the and this is the velocity. So I ask you kinetic energy. Obviously, this is again very basic. I'm just putting it very quickly. 1500 kg times velocity is 100 kilometers per hour. So then at the end, you have to convert them to joules. Okay, so that's where most of the students makes mistakes. So if you see what is the Joule formula, as you see, is Joule equal to this. So that's 1 newtons times meter. Okay, and that's equal to 1 joules. And if you see 1 newtons is equal to kilograms meter per second square. That's 1 newton as meter. So that will be kilograms meter square second square. Okay, that's equal to 1 joule. So if you think of this answer here, kilogram is there, the kilometers and hours are different units. To convert that, you have to change that to, so I'm just going to erase this one so that I can write that number. So 1 kilometers is 1000 meter, and 1 hour is 3600 second. Then you have now everything, hour cancel, kilometer cancel. So now this is meter square by second square. So whatever that answer is, then now you can change that to in joules. Okay, so that's the only problems here. Another example: a 75 kilogram person walks up a flight of stairs with a vertical height of 3 meters. What is the change in personal potential energy? So you start with one person start with here, and it climb to let's say 3 meters high. Okay. So after here, so what's the energy that that person lost? Potential energy. So that will be again, if you see this going against the gravity, so the force here is the gravity. So that's equal to mass times acceleration due to gravity. And if you, and displacement here is the difference is 3 meters. So that means the energy is force times distance, and that's mg, and distance is 3 meters. So mass is 75 kg. G is acceleration due to gravity, 9.8 meter per second square, 3 meter. So kg meter square per second square is joule. So that's all the answer would be. You don't have to change any units now. That will be in joules. All right, so thermal energy is the same again. On the here the difference is this is Boltzmann constant. That's basically the molecular the fact that they bombard with each other. So that vibration energy is that the small units is kT. So when you translate to moving molecules, that kinetic energy becomes that trapped in that unit form. So this is Boltzmann constant. It's written here. Okay, and that's related to that translate to thermal energy, temperature. So that's why when you heat up any air, so that's how the energy translate. The temperature rise because of that friction between molecules. So this is basically a 3/2 Boltzmann constants times temperatures. And temperature, the unit is degree Kelvin. Okay, so this is degree Kelvin, not the degree Celsius or degree Fahrenheit. So just make sure that's the units in your any questions in that. For a gas related to this, again, thermal temperature, so that's here. And the difference between here is that you just replace that with a natural gas constant. N is the moles and R is the gas constant. And so ideal gas law, that's how this is defined. If you convert that here, this is written here. This is the power. If you use the gas constant, all that. Okay, so again, I'm not really going through that very quickly because this is very simple, just formula. Okay, so let's use that to solve these questions. Thermal energy. Thermal energy is a flow rate divided by the total energy, heat energy divided by heat capacity. So that's written here. That's again thermodynamics. So let's think of a little bit what's the concept behind it, where you are going to apply. So think of when you store energy, a lot of times battery is expensive technology. You can store energy by algae, that's one way. You can store energy by pumping water to the high ground so that whenever it's needed, you can just let the gravity fall through it. And that's how you create these supermassive the turbines and get electrical energy. Another form of energy is actually heat energy. So you can trap the heat from any wastewater treatment plants or any locations by thermal power plants or all that stuff. So you can capture the heat, waste heat, and you can store that heat. So how much energy you can store because of that waste heat is where you can apply this. So when you apply certain amount of heat energy, it increases the temperature, and that increase in temperature depends on how much they can resist before it increases. So usually the easiest thing to do or the storage heat is if you have some substance that do not raise its temperature uh, uh, or it raises temperature very slowly by absorbing that energy, and that's how you can store the energy. And it turned out water is excellent form of um, storage of energy. That's why you see anytime you have the system to cool the system, you use water. Partly it's available everywhere, and also it has high capacity to store heat. And compared to what? Let's say compared to soil. Soil, if you heat it up, it quickly conduct the heat energy, and that's why it can increase the temperature very quickly. Whereas water, it doesn't really heat up that quickly compared to the sand or the soil. And that's one of the reason, if you see why we have the ocean itself is a biggest reservoir of heat energy, and that's kind of modulate the temperatures in the climate. So that's one of the reason. If you think of, if you are living in Santa Monica or UCLA, we don't get the very warm in the daytime, or we don't get too cold at the nighttime because the wind that comes from ocean. So ocean is the one which captures that energy. Whereas if you're living a little bit inland, let's say inland means in this context here, San Bernardino, let's say there you live, that's far away from the ocean. So that's why they heat up very quickly in the summer. So that's why the temperature is extremely high. And in the winter, they also lose that energy very quickly, and there is no ocean to regulate that temperature. So that's the whole idea of here. Specific heat capacity is about how much energy it can store per unit rise in temperatures per unit mass. So specific heat capacity is again, just going to write that here. Specific heat capacity. Again, this is thermodynamic. I'm assuming you'll know all this. How much energy stored per unit mass per delta increase in temperatures. Okay, so that means if you for 1 degree increase in temperature, how much energy it can store per 1 kilogram of water. So this is given over here. The specific heat capacity is a constant term, which is constant for every for a particular mass. So per here, example is a 4180. Again, the reason why water store a lot of energy is because of hydrogen bonding, because they can reorient it. And so when you supply that energy is stored because they can reorient it. That hydrogen bonding makes them absorb more energy because of that. Because that energy has to be supplied to break that hydrogen bonding. Okay. Only when you finish breaking entire hydrogen bonding, it start moving. Okay, that the whole boiling start coming. So again, these are all concepts what we learned before. All right, so let's apply here. The specific heat of water is 4,180 degrees, 80 joules per kilogram per degree Celsius. Calculate the energy required to heat 500 grams of water for 20 degrees Celsius, from 20 degrees Celsius to 80 degrees Celsius. Um, so let's see that answers. So again, energy required is written here. Energy equal to specific heat. So let's write specific heat equal to specific heat. Let's write this is S, specific heat. Okay, times um, mass of water times the rise in temperatures. That's what the answer is from here. And so specific heat is 4180 joules per kilograms per degree Celsius. So mass is 500 gram. Now again you have to change to kilograms, so that's I'm going to change it. 1000 gram is 1 kilogram. So that's the mass term. Temperature is 80 degrees Celsius minus 20 degrees Celsius. So this is again in degrees Celsius at the bottom, so that's why you don't have to change anything. So that's basically that answer will be kg cancel or that cancel, so that your answer will be in joules. Okay. We discussed this one. I'm just going to skim over it. And any types of molecule, if you think of carbon burning biomass, basically you are breaking the bond because you are producing carbon dioxide. That carbon is released, and that bond is when it's broken, it's released at temperature. So that's the reason it's the energy is chemical energy. So this is just one example over here. Now, when you burn ethanol, how much energy you get? And when you burn ethanol, how much energy you get? And you can see that the reason why people use octane, if you see for camping, use octane. The reason is it produces a lot more energy than ethanol over here per unit amount of mass. Nuclear energy, again, I explain it. The reason why nuclear energy exists is because of the protons. They come close together. It has neutrons, protons. They are really compact in a very small space. And there has to be some form of things that bind them or keep them together inside the nucleus. That's nuclear energy. So that can be released when you break the atoms, and it requires excessive energy to break atom. That's why the thermal or the power on the nuclear weapons, for that to activate, you also, there is another bomb that was released initially before it become activated. And then the fission bomb is also same way. It's to combine those two atoms together, it become even more energy needed. So that's why there has to be atomic weapon that goes off, before the hydrogen or the fission bomb will be combined. So this is just an example. This is where the mass of neutrons or protons is converted to energy, and the form of energy conversion is mc the mc square. So basically, here mass is translated to energy. Okay. So this is the amount of mass is lost during the fission or fusion reactions. So that's why it's pretty high energy, because there is a velocity which is light energy. So very high energy. And so electrical energy, you guys use all the time. So basically the current, move current, and the reason current moves from one to another place, which is electron, is because of potential difference. The same concept as water moving from A to B, because of potential difference between two height of water. So same thing here is the electric potential. And the way we measure current is basically ampere. That just shows that what's the how much amount of charge is being transferred per unit time, which is in this case Coulomb. So again, I'm not really going through all details. I'm just showing what's the number, how you can relate to it. So this is the because of like water, where it moves from high height to low height. Current move from high potential to low potential. So this is potential volt. Volt is the electric potential. So voltage times the amount of charge transfer here, Charge transfer is the same as flow of water, so that's how I keep the same unit here. If you multiply that, you get the energy. So that's how it is written. And the charge transfer is basically, on the written over here, all that. All right. So again, this is just to, you are all, I assume this is something you already know, so I'm not going to explain that to details. Um, and just to give you an idea what is voltage, voltage is another unit is current times the resistance, because like water, there is a resistance for conducting currents. So if you multiply current time resistance, it will get that. So just use that equations, okay? Just revise this one. So let's solve the example problem, because that's what you need to learn or remember again. So let's say, what is the energy used if 560 watt bulbs are on for 3 hours? So basically, if you are using 560 watt bulbs for 3 hours, what's the energy is being produced? So again, you know that energy over time equal to power. So energy equal to power times T, and power is here already given, is a 5 times 60 watt, okay, and time 3 hours. And if you want to make it joule, you know that joule is one is a watt second, okay. So 1 joule is watt times second. So that means you have to change this one to second. 3600 second. So watt times second is joule. So that means everything else here would be cancel out. This is would be joules. Okay. So what is the power used in a heater of this is the voltage volt or potential energy applied for a current. This is current. And what is the resistance of the heater? Well, voltage equal to IR. Okay, so if I'm asking R, then you can calculate voltage by current. Everything is given. Okay, and if you're looking for what is the power, so if you see the previous answer here, power equal to voltage time current. So everything else is given. So I'm just writing all these things. So all the units are given here, so you can check that all the units for answers. And the last one, which is a form of energy, is electromagnetic energy. Is basically we cover it. That's energy equal to Max constant, Planck's constant times the frequency. This is frequency of light. And frequency of light changes based on the color. Like the UV ultraviolet is the highest frequency, and red light is the lowest frequency in the visible range. So this is written here now. So that's what the answers are. Here the frequency. I wrote the frequency F here. That's why I just changed it. So the way to look at is the velocity of light always constant. If you increase the frequency, that means you are decreasing the wavelength. So that's the lambda. So that's the way to look for it. Again, we cover this one. Let's say applications. So this is one of the reasons, if you think of where it is applied. If you have lots of energy, it's very easy to interact. Okay, so that's why UV lights is used for many of the degradations, because it has so much energy that it can break the molecules or interact with or disinfect. So that's one of the reasons also UV lights cause cancer, because that's the things that react in our cell. That's one of the reasons why other energy is not very harmful for us. But if you go even bigger, bigger and the more and more wavelength, think of what comes here. After ultraviolet, you get X-ray. That's the reason. Ultraviolet, you get exposure every day. But X-ray, imagine you get that much X-ray. It's very difficult. That's why in airport, all these X-ray, you get very fraction of second. You don't get high amount. If you even go even smaller and smaller or higher frequency, it's gamma ray. Gamma ray is very dangerous. In fact, the gamma ray burst can kill the entire planet if we are exposed to that during that supernova explosion. So that's one of the things that uh, you might heard about this one for superhero movies where they send gamma rays or it becomes superhuman or superhero is born because they are exposed to gamma ray. So this is just another way to show that they get lots of energy. In the other side, if you have a low energy, that means it's not very reactive. And if it's not reactive, it can travel a lot longer. That's the reason radio waves are used for transmission of signals. Imagine sending the signals in ultraviolet. It will not even transfer more than few meters. But if you have radio wave, the wavelength is so high that it doesn't dissipate and you can transfer for long distance. That's why you see the initial radios are when they are made, they are use radio wave. That's the whole idea of it. So that you don't need that tower for many places and you can transmit that without any wire. And so all this application is there. In fact, if you think of why in why use red lights for traffic light, the reason is this: if you use red light, it doesn't get diminished. It can somebody can see from a long distance because of atmospheric fog or smog. They will not observe as much red light as they will observe any other form of light. That's the reason we use red light, because if you want somebody to stop, they have to see that to stop. And so this is just another applications, just to show why it is done. Again, I explained this one, why light energy, UV lights are used for damaged skin because it has more energy. Why red lights are used to stop signals is because somebody can see them from a distance without being worried about the red lights being, particularly in winter season when we have a lot of smog or fog, you still be able to see red light as much as any other lights because of the wavelength. So you use the extreme form of other lights. And the last few slides is all about energy conversion using thermodynamics. So this is just to show that energy transfer is internal energy plus the work done. Okay, so that internal energy is converted to heat energy, and then there is work done for all these things to happen. Energy cannot be created, cannot be destroyed. It can only transfer from one energy to another form of energy. So this is just example of quiz question, how it can change from one energy to another. For instance, if this picture, if you see what form of energy is being transferred, you are moving something, that's mechanical energy is being moved. There is a turbine, whether water or something else hit that, it rotated, or wind rotated or water rotated. And as long as you put that inside a magnet, you disrupt that magnetic field, and that disruption form the electric energy. So that's how you get the electric energy here. So if I ask these questions on quiz, what form of energy being transferred, you will say mechanical energy, you transform to electrical energy. Whereas in battery, you say chemical energy is transformed to electrical energy, because that's where things moves from another to another form. In solar panel, if the solar energy is transformed to electrical energy. So that's how you can, or electromagnetic energy is transformed to um, electrical energy. So all that stuff you have to remember, at least, think of what energy is being transferred. Energy conversion, again, we don't have to cover this one, just know that this is there are some always waste heat. You cannot transfer the entire heat. That's why the second law of energy conservation is there. So now that you know all these energy fundamentals, the things that we need to remember is that there are many ways to convert those energy. Combustion is the most common form of energy. That's aerobic, means you burn them. And in fact, from ancient world, like 10,000 years old, human always use combustion energy to get their energy. Only recently they use anaerobic or other form of energy. For instance, fermentations. That's basically the anaerobic digester, which many of you are using it. That's anaerobic digestion. And then also we have other method to convert biofuel. Combustion, this is just to show that you can burn something, it produces all the other things. That's just to show in the schematic. And the waste you receive, and you have incinerator, and you produce ash. That's the waste you have to deal with. But that energy is transferred to a steam boiler, so that that's the way it heat transfer the energy, thermal energy, to water. And that steam boiler means that warm molecule capture that energy. Warm molecule doesn't split, it just move, it become gas, and that steam will go to a turbine. This is kinetic energy. So this is, let's say, this is chemical energy, this is thermal, this is kinetic energy. And steam turbines, that's again kinetic energy or mechanical energy, you can say. And mechanical energy is transformed to electrical energy here. So electrical energy. And then you have other stuffs there, and then you have um, if there is you have to also capture the air pollutant, all that stuffs. So these are solid waste. And so that means you need a source of clean water, because the turbines or the condenser, if you have dirty water, it's going to cause problems, corrosion, all that. So that's why you use clean water. Another example, pyrolysis, where you burn them without oxygen, so that you form carbon, like black carbon, biochar, and you capture the energy, extra energy, and you produce the biofuel. So this is another form of. So some of you are using algae as a project. You can get the algae. The problem with that issues or pyrolyzing algae is the you have to dry them a lot. If you have, they're all moist. So if you use them all as it is, you have to use so much energy to just evaporate the water. So that's why it's not very efficient to use pyrolysis for algae unless you have a way to dry them and make a biomass. But it's possible. Then another one is plasma arc classification. The idea here is that if you burn them slowly, you are forming these smaller molecules, okay, and that is the form of pollutions, the air pollutant. If you use very high temperature, you are not really using that intermediate product. You are using directly carbon dioxide, because if you use really high temperature, all carbon bond will break. There is no way that you can make this big molecule form smaller molecules and produce those smaller other pollutants. So that's the whole idea of here. You are creating a very extreme temperature to begin with, so that you form the carbon dioxide or the smaller molecules. So this is just to give you a different idea of what temperatures are needed and how much energy it can produce at the end. So this is just for comparisons. So that's all in terms of energy. So this, I hope that this give you at least some basic understanding of how to calculate energy, how to correlate that energy transfer for different applications. So this class is very important for your quiz on week 9. Or which will be next week. Next week, yes. So just read these slides so that you understand it. Okay, so I think that's all. But if you have any questions, I'll wait for a few more minutes. I see there is nothing in the chat window. So I'm going to stop recording.